On October 2nd, something fast, incredibly fast, streaked across the Martian sky. An amateur astrophotographer named Stefan Burns noticed it in NASA's raw Perseverance rover images. He created a time-lapse, 9 minutes of data, compressed. And there it was, moving at 60 kilometers per s against the normal motion of the stars. But here's where it gets weird. Other users started analysing the same images, and they claimed to see multiple objects, not just one, multiple fast-moving anomalies in the October 3rd data, plus a mysterious green flash that nobody can explain. NASA scheduled this observation. Multiple Mars orbiters were supposed to capture the closest images ever taken of an interstellar object. The higher camera capable of 30 kilometers resolution, the SS Mars Express, the ExoMars Trace Gas Orbiter, all pointed at 3 Atlas during its October 3rd flyby. And then, silence. No official images. No data release. Nothing. Meanwhile, Harvard's Avibi just published something that's making the entire astronomical community uncomfortable. This Object 3 Atlas might have been the source of the famous 1977 WOW signal. The chance of that being coincidence, 0.6%. But the WOW signal connection is just the beginning, because 3 Atlas is breaking every single rule we have for how comets behave. It's producing industrial-grade nickel alloys in space. Its tail points the wrong direction. It's green when it shouldn't be green. And it's following a trajectory so perfectly aligned with our planet that the odds are astronomical. Some are calling it the largest interstellar object ever detected. Others are calling it impossible. Heavy Lobe is calling it potentially artificial, and right now it's behind the sun where we can't see it. Hidden, approaching its closest point to our star. What happens when it comes back out before we dive deeper? If you're finding this fascinating, hit that like button and subscribe so you don't miss what's coming next. And tell me in the comments where you're listening from, what time it is there, and whether you think we're seeing one object or multiple. And if you want to help this community grow, share this on X, Facebook, Reddit, or your messenger. Thank you for always having our back. Chapter 1. Wait. There are multiple objects. Let's go back to October 2nd. Stefan Burns wasn't looking for anything extraordinary. He was simply processing the raw image data that NASA makes publicly available from the Perseverance rover. The rover had been instructed to observe the night sky during a specific window. The window when 3 Atlas was predicted to pass closest to Mars, closest being a relative term. We're talking about 29 million kilometers of separation. Burns took 9 minutes of consecutive images and stacked them into an animation in astrophotography. This technique reveals motion that would be invisible in a single frame. Stars appear to move across the frame due to Mars' rotation. But this was different. Something was cutting across that motion at an angle that made no sense for a background star. The speed was the first clue. At 60 kilometers per s, 3I Atlas moves faster than nearly anything in our solar system. For comparison, Earth orbits the Sun at about 30 kilometers per s. The Parker Solar Probe, humanity's fastest spacecraft, reaches 192 kilometers per s only at its closest approach to the Sun. But 3 Atlas maintains this blistering pace throughout its journey. Burns posted his animation online. Within hours, other amateur astronomers began their own analysis. And that's when someone named Nachtaf, a German username meaning night monkey, made a claim that sent ripples through the observing community. In the pictures from October 3rd, Nachtaf wrote, "You can even see multiple comets. Not one object, multiple." Another user, Alexander Pum, pointed out something else. What is the flash at second 0003 marked with green? Go back and watch Burns's animation frame by frame. There, at the 3-second mark, a brief green luminosity appears. It's not a camera artifact. It's not a cosmic ray hit which would appear as a single bright pixel. This is a diffused glow, localized but distinct. Green light in space has specific causes. On Earth, we associate it with auroras with copper burning with certain bioluminescent organisms. In space, green emission typically comes from oxygen or from a molecule called dicarbon. Two carbon atoms bonded together. Comets sometimes glow green when solar radiation excites dicarbon in their comas. But here's the problem. Spectroscopic analysis of 3E Atlas from the Very Large Telescope showed virtually no dicarbon. The object is what astronomers call chain-depleted. It shouldn't be glowing green. Yet photographs from ground-based telescopes in early September clearly showed a green hue developing around the object. The green flash in the Mars images, if real, adds another layer to this mystery. Now, about those multiple objects, this is where things get speculative. But the speculation is coming from people with telescopes and image processing software, not from people making things up. When you stabilize the star field in Burns's animation, when you account for Mars's rotation and the motion of the primary object, there appear to be at least one or two additional points of light moving at different velocities. Could these be imaging artifacts? Absolutely. Could they be background asteroids that just happen to be in the frame? Possibly. Could they be separate fragments or even smaller objects accompanying 3I Atlas? That's the question nobody can answer yet because NASA hasn't released the data. The Mars Reconnaissance Orbiter's HiRISE camera observed 3 Atlas on October 2nd between 1 and 4 in the morning, Mars local time. The ESA's Trace Gas Orbiter and Mars Express both captured observations on October 3rd. These weren't casual snapshots. These were coordinated, pre-planned scientific observations designed to gather the highest resolution data ever obtained of an interstellar object. HiRIS, the high-resolution imaging science experiment, can resolve features as small as 30 centimeters on Mars's surface from orbit. When pointed at an object 29 million kilometers away, it should still achieve a resolution of about 30 kilometers per pixel. That means if 3E Atlas has a nucleus 5 kilometers across, as recent estimates suggest it should appear as a bright cluster of pixels in the HiRISE images. More importantly, Heresy would be able to distinguish between a single compact nucleus and a fragmented or multi-component object. If there are multiple pieces, if there's a companion object, if there's anything unusual about the structure, would see it. So where are the images? NASA's official statement has been minimal. The Mars orbiters successfully conducted their observations. Data is being processed. Updates will be provided as analysis continues. That was over 24 hours ago. In the world of space imaging, 24 hours is plenty of time to at least preview raw data. Some observers have noted that the United States government has been dealing with various administrative issues that have affected the release of scientific data. But ESA operates independently. They should have no such constraints. Yet, ESA's images haven't appeared either. The silence feels deliberate, and when official channels go quiet, amateur observers start talking. Because here's what we know for certain. The Perseverance rover did capture something. Multiple amateur analysts examining the same publicly available raw data are seeing anomalies. The object or objects moved at velocities consistent with 3E Atlas. And there's that green flash that no one can explain. What we don't know is whether those apparent multiple objects are real, whether they're separate from the main comet and what NASA and ESA saw with their far more powerful instruments. The October 3rd flyby represented the closest any spacecraft has ever come to an active interstellar object. This was our chance to understand what 3Psi Atlas really is, to see its structure up close, to determine if it's behaving like a normal comet or like something else entirely. And as we wait for answers, the object itself continues its journey. Right now, it's approaching the Sun, moving deeper into the inner solar system, where Earth-based telescopes lose sight of it against the solar glare. By late October, It will pass behind the Sun from our perspective, completely hidden, and when it emerges in November or December, it will either confirm every natural explanation, or it will have done something that comets simply don't do. But before it vanishes, we need to talk about what the Mars observations were really looking for, and why the timing of this silence matters more than you might think. Chapter 2. The Mars Blackout. There's a pattern in how space agencies handle sensitive observations. When something routine is captured, the data appears within hours. Raw images populate public databases. Press releases get drafted. Scientists tweet their findings. When something unexpected appears, the silence stretches. The technical explanation for the delay centers on data processing pipelines and calibration requirements. Mars orbiters don't transmit images in real time. They store observations on board, then beam them to Earth during scheduled communication windows. From there, the data moves through various processing stages: geometric correction, radiometric calibration, noise filtering. For a typical surface observation, this takes 6 to 12 hours. For a moving target against the starfield, maybe twice that. We're now well past 48 hours since the October 3rd observations. But there's another factor at play, one that doesn't get mentioned in official statements, but filters through the community of researchers who depend on NASA data for their work. Budget constraints and administrative disruptions have created bottlenecks in data release protocols. Not a formal shutdown, but the kind of bureaucratic friction that turns routine processes into delayed ones. Staff working reduced hours, priority systems getting reshuffled, review chains lengthening. ESR operates under different administrative structures, yet their Mars Express and ExoMar Trace orbiter images haven't appeared either. This suggests either a coordinated decision to withhold preliminary data until full analysis is complete, or technical challenges that both agencies are working through simultaneously. The question becomes what would be challenging enough to cause this delay. Consider what these instruments were designed to see. The color and stereo surface imaging system CASes on the Trace Gas Orbiter can resolve features down to about 4.5 meters per pixel when imaging Mars pointed at an object 29 million kilometers away. That resolution drops significantly, but the instrument's sensitivity remains high. It's designed to detect subtle color variations in Martian surface materials. If 3E Atlas was shedding multiple types of ice, if its coma showed compositional variations, if there were structurally distinct regions, CASIS would capture that. Mars Express carries the high-resolution stereo camera, which, despite its name, focuses on three-dimensional topography. For a distant comet, its stereo capability matters less than its ability to image across multiple wavelengths simultaneously. The camera can distinguish between dust, water ice, carbon dioxide ice, and various minerals based on how they reflect different colors of light. Then there's the Mars Reconnaissance Orbiter's HiRISE, which we've mentioned. But here's what we haven't discussed. HiRISE doesn't just take pictures. It collects data across 3 color bands: blue, green, red, and near-infrared. When pointed at a comet, those bands reveal different aspects of composition and activity. Blue-green light interacts with gases in the coma. Red and near-infrared red penetrate through thin dust, revealing structure beneath. If the comet was releasing jets of material from specific locations on its nucleus, if those jets had different compositions, if the brightness varied across the objects in ways that suggested a non-uniform surface, HiRISE would document all of it. And here's the thing about sensitive images. They sometimes show features that require consultation before release, not because of conspiracy, but because preliminary observations can be misinterpreted without proper context. If HiRISE captured something that looked unusual, mission scientists would want to rule out instrumental artifacts, cosmic ray hits, or processing errors before making the data public. But while we wait for official channels to open, there's Simeon Schmaus. Schmaus is an astrophotographer who specializes in processing raw planetary data. He's known in the community for his ability to extract signal from noisy images to stabilize shaky video to bring out subtle features that initial processing misses. On October 1st, a day before Stephen Burns's October 2nd time-lapse, Perseverance captured a series of night sky images. These were posted to NASA's raw image database. As all Perseverance images are, within hours of being received on Earth, Schmaus downloaded them, applied his processing techniques, and claimed to see an early glimpse of Three-Eye Atlas in those frames. The claim hasn't been independently verified. The object would have been extremely faint at that distance and angle. But if legitimate, it suggests the comet was detectable even before the main observation window. More intriguingly, Schmaus noted that the motion he detected didn't perfectly match the predicted trajectory. Close, but with a slight deviation. He posted his findings on social media, stating that more analysis was needed, but the preliminary results were intriguing. Then, like the official sources, he went quiet. Whether he's still analysing, whether he found something he wants to confirm before discussing publicly, or whether he's been asked to hold off, we don't know. What we do know is that there's a gap between what should be routine disclosure and what's actually happening, a gap between the scheduled observations and the data we can examine, a gap that's filled with amateur discoveries, unexplained green flashes, and claims of multiple objects that nobody can officially confirm or deny. The Perseverance rover continues its surface mission. Its cameras remain functional. Its data continues uploading to the public database. But the specific images from those crucial nights, the ones that matter most, are the ones being scrutinized in silence. By October 29th, 3 Atlas will reach perihelion, its closest approach to the Sun. At that point, it will be entirely behind our star from Earth's perspective, invisible to ground-based telescopes and space-based observatories alike. The window for observation is closing. Whatever NASA and ESA saw, whatever Schmaus found, whatever is happening behind the review processes and data pipelines, the clock is running. Because if there's something unusual about this object, if those multiple points of light are real, if the green flash means something, we need to know before it disappears into solar glare. And if we don't get those answers, we'll have to wait until November when the comet emerges on the other side, potentially changed by its close encounter with the Sun, potentially having done something that natural comets don't do. But there's another reason the timing matters. Because while we've been focused on what the Mars observations might show, Avi Lobo has been looking backward, tracing 3-Eye Atlas's path, not just through our solar system, but through time. And what he found connects this object to one of the most famous unexplained signals in the history of astronomy. Chapter 3, The WOW Signal Bombshell, August 15th, 1977. Ohio State University's Big Ear radio telescope was conducting a routine survey of the sky, searching for signals that might indicate technological civilizations beyond Earth. The telescope operated automatically, scanning narrow bands of radio frequencies, printing out intensity readings on continuous paper. Astronomer Jerry Ayen was reviewing the printouts 3 days later when he noticed something that made him grab at a red pen. A signal had appeared, strong and narrow band lasting exactly 72 seconds. The intensity was so far above background noise that airmen circled the alphanumeric sequence and wrote one word in the margin: WOW. The signal came from the direction of Sagittarius near the globular cluster M55. It was detected at a frequency of 1,420 MHz, which sits within the protected radio astronomy band. No human transmissions are allowed at that frequency. The signal's bandwidth was narrow, less than 10 kos, exactly what you'd expect from an artificial transmitter rather than a natural astronomical source. The Big Ear never detected again. Follow-up observations found nothing. For nearly 50 years, the WOW signal has remained one of astronomy's deepest mysteries until Avibi decided to calculate where 3I Atlas was on that date. Working backward from the object's current trajectory and velocity, Low traced its path through space. In August 1977, 3I Atlas would have been approximately 600 astronomical units from Earth. That's 600 times the distance between Earth and the Sun, far out in the outer reaches of the solar system, but not yet in true interstellar space. The WOW signal originated from sky coordinates of right ascension 19 hours 25 minutes declination minus 27 degrees. These coordinates point towards Sagittarius. Loeb calculated 3 Atlas's position on August 15th, 1977. The object would have been at right ascension 19 hours 21 minutes declination, 19 degrees, 4 degrees separated in right ascension, 8 degrees in declination. In astronomical terms, that's remarkably close. The chance of 2 random directions in the sky aligning to within 9 degrees of each other, about 0.6%. But alignment alone doesn't prove causation. Low went further. If 3I Atlas transmitted the WOW signal, how powerful would the transmitter need to be? The signal intensity detected by Big Ear ranged from 54 to 212 Janskis. A Jansky is a unit measuring radio flux density. For comparison, the strongest radio sources in the sky like the Sun or Jupiter typically measure in the hundreds to thousands of Janskis when observed at specific frequencies, at a distance of 600 astronomical units. Generating the received intensity would require a transmitter outputting between half a gigawatt and 2 GeV of power. That's the output range of a typical nuclear power reactor on Earth. Not impossible. Not even particularly advanced by the standards of a civilization capable of interstellar travel. But notable because it's precisely the kind of power budget that would make sense for a deep space probe trying to communicate across vast distances. There's another detail. The WOW signal showed a slight frequency shift. It was detected at 1420.4556 MHz, which is about 10 kHz higher than the neutral hydrogen line frequency. This represents a blue shift, meaning the source was moving toward Earth. 3I Atlas is moving toward the Sun at approximately 60 km/s. When you account for Earth's motion and geometry in August 1977, the relative velocity would produce a blue shift. Low calculated the expected shift. It's close to what was observed, though not a perfect match. The difference could be explained by uncertainties in the exact position and velocity vectors, or by the signal having been transmitted in a specific direction rather than omnidirectionally. Here's where it gets interesting from a strategic standpoint. If you're an intelligence wanting to announce your presence, broadcasting near the hydrogen line makes sense. Hydrogen is the most abundant element in the universe. The 21 centimeters hydrogen line is so fundamental to radio astronomy that any civilization capable of radio technology would monitor it. It's the galactic calling card frequency. The WOW signal lasted 72 seconds because of how the Big Ear telescope operated. It used 2 feed horns separated in the sky that listened to adjacent regions as Earth's rotation swept them across the target. Each feed horn had a window of 36 seconds. The signal appeared in both horns sequentially, creating the 72-second detection. This means the source was transmitting continuously, or at least for the duration that Big Ear could observe it. Not a brief pulse, but a sustained broadcast. If 3 Atlas was responsible, this raises immediate questions. Was it a beacon announcing presence to anyone listening? Was it a navigation pulse marking position for some other spacecraft? Was it an attempt at communication? Encoding information we lack the sophistication to decode? Or was it entirely unrelated? A cosmic coincidence where an interstellar comet happened to be aligned with a natural radio source we haven't yet identified. The problem is we don't have radio telescope data on 3 Atlas. Not from August 1977, obviously, but not from now either. No observatory has reported pointing radio dishes at this object. The focus has been on optical observations, on spectroscopy, on imaging. The questions being asked are about composition and structure, not about whether it's transmitting. Lowe is arguing that needs to change immediately. The object is approaching perihelion. It's getting closer to the sun, which means higher temperatures, more activity, more energy available if there's any kind of technological system involved. If it transmitted once at 600 astronomical units, if it's designed to communicate at specific points in its journey, this would be the time. Radio telescopes like the Very Large Array in New Mexico, the Arecibo successor facilities, even the vast arrays in China and Australia could monitor 3 Atlas across multiple frequencies, not just the hydrogen line, but across the spectrum where artificial signals might appear. The observation would be straightforward. Point. Listen. Compare to background. Look for any narrow band signals, any modulation patterns, any repetitive structures that natural sources don't produce. If there's nothing, fine. It costs a few hours of telescope time to rule out the hypothesis. But if there's something, if 3E Atlas is emitting radio signals, even faint ones, even intermittent ones, that changes everything about how we interpret this object. Because a comet doesn't broadcast, a chunk of ice and rock, even from another star system, doesn't generate radio signals at specific frequencies. Natural astronomical sources produce radio emissions, but they're broadband chaotic, lacking the structure that indicates intention. The WOW signal had structure. It had a narrow bandwidth. It appeared at a meaningful frequency. And if Avi Lobo is right about the alignment, if the 0.6% 6% coincidence is actually causation, then somewhere in the outer solar system 48 years ago, something transmitted a signal powerful enough for us to notice. That something is now racing past Mars, hidden behind the sun from our perspective, doing things that comets aren't supposed to do. The question isn't whether we should be listening. The question is why we aren't already. Chapter 4. It's making industrial alloys in space. When comets approach the sun, they begin to shed material from their surfaces. Ice sublimates directly from solid to gas. Dust particles lift off. Trapped volatiles escape, and occasionally, if the comet gets hot enough, trace amounts of metals vaporize from the dust grains embedded into the ice. Nickel and iron appear together in these outgassing plumes, always together because they form together in stellar processes, exist together in meteoritic material, and sublimate at similar temperatures. The ratio varies slightly from comet to comet, but it follows a predictable pattern. For every atom of nickel you detect, you expect to see about 10 atoms of iron. The previous interstellar comet, 24/Boros, followed this rule perfectly. Solar system comets follow it. Every icy body we've observed that shows metal emission follows it except 3E Atlas. The European Very Large Telescope in Chile has been observing this object with its ultraviolet and visual shell spectrograph, an instrument designed to split light into its component wavelengths with extraordinary precision. Between August and September, observers captured spectroscopic data across 6 time periods as the comet moved from 3.14 astronomical units down to 2.14 astronomical units from the Sun. In every observation window, nickel emission lines appeared in the spectrum. Bright, clear, unmistakable. Iron appeared only when the comet got closer than 2.64 astronomical units. Before that threshold, nickel without iron. After it, nickel with some iron, but in ratios completely unlike anything seen in other comets. The nickel-to-iron ratio measured orders of magnitude higher than solar abundance ratios, higher than typical cometary ratios, higher than natural geologic processes would produce. The production rate made it even stranger. 3I Atlas was releasing nickel gas at approximately 5 g per s when first observed. As it got closer and warmed up, that rate increased dramatically. 5 g per second doesn't sound like much until you consider what it means. That's 430 kilograms per day, over 3 tons of nickel per week from an object that's supposed to be made primarily of water, ice, and rock. The surface temperature at 2. 8 astronomical units where much of this emission was observed sits far too low to vaporize silicate minerals or metallic grains that would contain nickel and iron. The comet would need to be at least twice as close to the Sun for normal sublimation of refractory materials to occur. Something else is happening. The research team proposed several possibilities. Perhaps nickel exists in a form that releases easily. Nickel tetracarbonyl, a volatile compound, breaks down under ultraviolet light and would release free nickel atoms into the coma. But forming nickel tetracarbonyl requires specific chemistry at specific conditions, specific pathways that aren't common in natural processes. On Earth, we produce nickel tetracarbonyl industrially. It's part of the bond process used to purify nickel from ore. You heat impure nickel with carbon monoxide at specific temperatures and pressures. The nickel forms gaseous nickel carbonyl. You then decompose it at higher temperatures to deposit pure nickel. The chemical signature of 3 Atlas, releasing nickel without corresponding iron, mimics the output of this industrial refining process. There's another possibility the researchers mentioned. Perhaps the nickel is embedded in organic compounds or exists as nanoscale particles that respond differently to solar heating than bulk metal grains. Perhaps photon-stimulated desorption, where light directly kicks atoms off the surface, is somehow preferentially releasing nickel. These are plausible natural mechanisms, complex, requiring specific conditions, but possible. Except here's the thing about natural mechanisms. They leave evidence. They require precursor materials. They depend on the comet's formation history, its journey through space, the radiation environment experienced. 3 Atlas likely formed in the Milky Way's thick disk, a region of older metal poor stars. Models suggest it spent between 4 and 7 billion years travelling through interstellar space before entering our solar system. During that journey, it would have been exposed to cosmic rays, to background radiation, to collisions with interstellar dust and gas. Could that exposure have created surface chemistry exotic enough to explain the nickel emission? Could the comet have accumulated material during its journey that now, heated by the sun, releases metals in unusual ratios? You'd expect comets that formed around different stars to show chemical differences. Different protoplanetary disks have different compositions, the mix of elements, the ratio of volatile to refractory materials, the structure of organic molecules. All of this varies based on where and when a solar system forms, but the laws of physics don't change. Nickel and iron still form together in supernova. They still condense together in protoplanetary disks. They still sublimate at similar temperatures. Getting them to separate to release in dramatically different ratios requires overcoming fundamental chemical relationships. Unless the nickel isn't sublimating from ice and rock, unless it's being released through a process that involves chemistry we don't typically associate with comets. Lowe predictably has pointed out that the observation matches what you'd expect from artificial nickel production. Not that the comet is a factory, but that if it were a technological object with nickel-based components or a nickel-rich surface coating accumulated during interstellar travel, solar heating could ablate that material. The lack of iron would then simply reflect the composition of whatever is being eroded. The counter-argument is straightforward. Why would an advanced civilization build something out of materials that ablate so easily if you're designing an interstellar probe to last billions of years? You don't use materials that start vaporizing the moment you get near a star. Unless the vaporization is intentional, unless releasing a plume of material serves some purpose. Cooling, perhaps mass shedding to adjust trajectory, signal generation, creating a visible marker that can be observed from a distance, or unless the coating accumulated during the journey wasn't part of the original design. Interstellar space isn't empty. At 60 kilometers per s, even diffuse gas and dust particles impact with significant energy. Over millions of years, a spacecraft would accumulate surface material just like a comet does. If that material happened to be rich in certain elements based on what regions of the galaxy the object traversed, you might see unusual compositions. The Very Large Telescope data doesn't prove any of this. It simply establishes that 3I Atlas is behaving anomalously. The nickel without iron, the extreme production rates, the timing of when different emissions appear, none of it fits comfortably into our models of how comets work. And nickel is just one piece, because while the VT was documenting metal emissions, the Hubble Space Telescope was capturing images that revealed something even more fundamental, something that challenges the very definition of what a comet is. Chapter 5. The Anti-Tail Anomaly. Comet tails point away from the Sun. This is one of the first things you learn about comets, not because they're following the comet's motion, but because they're being pushed by solar radiation and the solar wind. Photons carry momentum. When billions of photons per second strike dust particles and ionize gas molecules, they transfer that momentum outward, creating the characteristic tail that always streams away from our star. Direction is so fundamental to comet behavior that when astronomers spot a comet, they can immediately determine which way the Sun lies just by looking at where the tail points. On July 21st, the Hubble Space Telescope captured the highest resolution image yet obtained of 3 Atlas. The comet was 277 million miles from Earth, still inbound toward its October perihelion. The image shows a diffuse glow ahead of the object pointing toward the Sun. The glow is elongated roughly 10 times longer than it is wide, forming a teardrop or jet-like structure. Behind the object in the direction where a tail should be streaming, there's nothing. No bright plume, no extended dust trail, just the faint gradient of scattered light fading into background darkness. The glow is an anti-tail. Now, anti aren't completely unknown in solar system comets, sometimes under specific geometric conditions. When Earth passes through a comet's orbital plane, we see dust that's been left behind in the comet's orbit, stretching out in front of the comet from our viewing angle. It's an illusion of perspective. But 3E Atlas isn't in this geometric configuration. The viewing angle doesn't support a perspective effect, and the brightness profile of the forward glow doesn't match what you'd expect from orbital dust. David Jewett, an astronomer at UCLA who led the Hubble observations, analysed the surface brightness as a function of distance from the nucleus. In a normal comet coma, brightness falls off gradually. Dust spreads out, dilutes, and the intensity drops following a gentle power law. The forward glow of 3I Atlas drops with a projected power law slope of -3 that corresponds to a 3-dimensional emissivity profile with a radial slope of -4. This is steeper than observed in typical solar system comets, much steeper. A steep fall-off suggests that whatever is creating the glow is concentrated near the source and dissipates rapidly. Either the material is extremely fine-grained and quickly pushed away by radiation pressure, or there's active jetting from a specific location on the nucleus creating a directed plume. DeWitt's team interpreted this as dust evaporating from the sunward side of the comet. Solar heating would be strongest on the hemisphere facing the Sun. Ice sublimates. Dust lifts off. The dust cloud expands forward before radiation pressure begins to push it back. It's a reasonable interpretation. but it requires the comet to be shedding material asymmetrically, with the sunward side dramatically more active than the rest of the surface. That level of asymmetry is unusual, but not impossible. What's harder to explain is the absence of a dust tail. If dust is being lifted off the surface in quantities sufficient to create the visible forward glow, that dust should persist. Radiation pressure would push it outward. The comet's motion would draw it back into a tail, and we should see something. Unless the dust particles are extremely small, particles smaller than a few hundred meters interact so strongly with light that they are blown away from the comet almost immediately, creating a faint haze rather than a distinct tail. But such small particles also get destroyed quickly by solar radiation, breaking down into even smaller fragments until they are essentially invisible, or unless most of what we're seeing isn't dust at all, but gas. Gas doesn't form persistent tails the way dust does. It disperses, thins, becomes transparent once it moves far enough from the nucleus. But if it's primarily gas creating the forward glow that brings us back to composition questions, what gas at what rate? And why so concentrated in one direction? There's another possibility that Lowe and his colleague Eric Cato explored in a paper. If 3I Atlas is generating its own light rather than just reflecting sunlight, the brightness profile would look different. Internal energy sources, whether from radioactive decay or some other process, would create emission that falls off steeply with distance simply because you're moving away from the source. This isn't as wild as it sounds. Some comets show faint air glow in their comas, emission from molecules excited by solar ultraviolet light. But those emissions are well characterized. We know what wavelengths to expect, what intensities, what structures. The Hubble image is broadband. It captures light across a range of wavelengths. Without spectroscopy of that specific forward glow, we can't determine whether it's purely reflected sunlight or includes some emission component. What we can say is that the structure is anomalous. Forward-directed, steep fall-off, no corresponding tail. These features together create a picture that doesn't fit standard comet models without invoking special circumstances. And here's what makes it important. The orientation of this jet or plume or whatever we're calling it points in the direction of motion. The comet is travelling toward the sun and the glow extends ahead in that same direction. If you wanted to design a braking system for an interstellar object, releasing material forward would create thrust in the opposite direction. It's not efficient compared to rocket propulsion, but over long time scales with continuous mass loss, it could produce measurable deceleration. 3I Atlas has shown no measurable non-gravitational acceleration. Multiple teams have analysed its trajectory, compiled thousands of positional observations, and found motion consistent with gravity alone. But that analysis has limits. Small accelerations below about 15 m per day squared would be lost in the noise, and the observation window is relatively short. The comet was only discovered in July. We've tracked it for a few months across a portion of its orbit. If it were decelerating slowly, gradually adjusting its trajectory through directed mass loss, we might not detect it yet, or the forward jet might be entirely natural, the result of how ice sublimates from a rapidly spinning nucleus with an irregular shape. The image alone can't tell us, but combined with the other anomalies, the nickel emissions, the chemical composition, the trajectory, it adds to a pattern where each individual observation can be explained naturally. But the collective picture becomes increasingly strained. You can have a comet with unusual chemistry, you can have one with an odd trajectory, you can have one that ouches asymmetrically, but having all of these features in a single object, the third interstellar visitor we've ever detected, starts to push against statistical expectations, especially when you calculate just how massive this thing actually is. Chapter 6, 33, billion tons of mystery. When an active comet releases gas and dust, physics demands a response, action and reaction. Material ejecting from the surface creates thrust. Not much, but measurable. A typical comet might experience non-gravitational acceleration of a few hundred meters per day squared, over weeks and months. This causes the trajectory to deviate from a pure gravitational path. Astronomers use these deviations to estimate how much mass a comet is losing, and by extension how massive its nucleus must be. More massive objects resist acceleration. A small nucleus shedding material will veer noticeably. A large one barely budges. Between May 15th and September 23rd, 227 observatories worldwide tracked 3I Atlas. More than 4,000 individual position measurements were compiled at the Minor Planet Center, the International Clearinghouse for Small Body Observations. Richard C.L.U., Peter V. and Avi Loeb analyzed this data set. They fitted the observations to a purely gravitational trajectory, calculating where the comet should be at each moment, based solely on the sun's gravity and perturbations from planets. Then they look for deviations. The upper limit on non-gravitational acceleration came out to less than 15 m per day squared. Perhaps much less. Perhaps even 0, but certainly below that threshold. This is astonishingly small for an active comet that's visibly outgassing. The James Webb Space Telescope detected carbon dioxide escaping from 3E Atlas at roughly 150 kilograms per s in early August. That's 13 tons per day. As the comet moved closer to the Sun through September, that rate likely increased. When you eject mass at high velocity, conservation of momentum dictates that the remaining object experiences a force. The gas coming off the surface has an outflow velocity around 440 m per s, measured by Webb spectroscopy. Plug in the numbers, multiply mass loss rate by velocity, divide by the comet's mass. The result tells you how much the comet should accelerate. If 3I Atlas showed negligible acceleration despite this continuous mass loss, its nucleus must be massive enough that the thrust becomes undetectable in the observational noise. The calculation yields a minimum mass of 33 billion tons. Think about that number. The first interstellar object, Oumuamua, had an estimated mass somewhere between 10 million and 100 million tons, depending on assumptions about its density and shape. The second 2I Boris likely weighed a few hundred million to a few billion tons, based on its brightness and activity level. 3I Atlas is at least 33 billion tons, potentially more since that's just the lower limit. It could be 10 times heavier and still fit the observations. This makes it 1,000 to 1,000,000 times more massive than the previous interstellar visitors. And here's where the statistics become uncomfortable. Models of how interstellar objects form and get ejected from planetary systems predict a size distribution. Small objects should vastly outnumber large ones. This isn't arbitrary. It's based on what we know about planet formation, about gravitational interactions, about how material gets flung out of solar systems. For every kilometer-scale object floating through interstellar space, there should be thousands of objects 100 m across. For every 100 m object, thousands more at 10 m, the distribution follows a power law. When we discovered one Oumuamua roughly 100 m in size, that was expected. Small objects are common. They're harder to detect because they're faint, but with telescopes scanning the sky continuously, we should find them. 2I Boris, larger and more active, fit the same framework. Bigger than Oumuamua, but still within the range of what models predicted we'd encounter. 3I Atlas breaks the pattern. Its minimum diameter based on that 33 billion ton mass estimate exceeds 5 kilometers. More realistically, given what we know about cometary densities, is probably between 5 and 10 kilometers across. Objects this large should be extraordinarily rare. The models suggest we ought to detect somewhere between 10,000 and 100,000 smaller interstellar objects before encountering one this massive. We've detected two. Lowe calls this a major anomaly. The Fraser sells it. If 3E Atlas truly is 5 plus km across, and we're seeing it as only the third interstellar object ever identified, either our models of interstellar object populations are catastrophically wrong, or we're exceptionally lucky to the point of statistical absurdity or 3. I-Atlas isn't a random sample from the expected population. The lucky hypothesis requires believing we hit a 1 in 10,000 or worse chance. Possible but uncomfortable. The wrong models hypothesis means rethinking fundamental assumptions about how planetary systems form and evolve, about how objects get ejected into interstellar space, about the mass distribution of debris wandering the galaxy. Not impossible, but it would require major revisions to theories that work well for everything else we observe. The non-random hypothesis suggests 3I Atlas is unusual for reasons beyond statistics. Perhaps it formed through a rare process that produces large objects more frequently than standard planet formation models predict. Perhaps it's a planet-forming seed, as some researchers have proposed, a large solid core ejected early in a solar system history. Or perhaps it's following an intentional trajectory that brought it here, making its detection not a matter of chance, but of design. That last option is what makes most astronomers uncomfortable. Not because it's impossible, but because accepting it requires abandoning the principle that says we should exhaust natural explanations before invoking extraordinary ones. But here's the tension. At what point do the natural explanations become more extraordinary than the alternative, a comet that's 1 million times more massive than expected, that produces industrial metal signatures, that jets material forward with no backward tail, that glows green without the molecules that cause green glow, that aligns with a famous radio signal to within 1% probability, that follows a trajectory passing remarkably close to multiple planets? Each anomaly has a potential natural explanation. The combination strains credule, and we still haven't discussed a single most bizarre aspect of its chemistry, the discovery that made headlines precisely because it violated every rule we have about what comets contain. Chapter 7, The Chemical Nightmare. On August 6th, the James Webb Space Telescope pointed its near-infrared spectrograph at 3 Atlas. Webb operates above Earth's atmosphere, free from the water vapor and carbon dioxide that plague ground-based infrared astronomy. Its instruments can detect molecules that would be invisible to telescopes on the surface. The spectroscopy revealed carbon dioxide, water, carbon monoxide, and carbonyl sulfide in the comet's coma. All expected for an active comet, but the ratios were profoundly wrong. The carbon dioxide to water ratio measured 8:1. In every other comet ever studied, including the previous interstellar visitor 2 of Borisov, water dominates. Carbon dioxide exists as a minor component, typically making up 5 to 20% of the volatile inventory. Water ice forms the bulk of cometary material because water was abundant in the protoplanetary disks where comets formed. 3I Atlas inverts this completely. For every molecule of water, there are 8 molecules of carbon dioxide. By mass fraction, the coma is roughly 87% carbon dioxide, 9% carbon monoxide, and only 4% water. This ratio sits 6 standard deviations above the typical value for solar system comets. In statistical terms, that's not an outlier. That's a different population entirely. Martin, the astronomer who led the Webb observations, noted that such a high carbon dioxide content could indicate the comet formed near the carbon dioxide ice line in its parent protoplanetary disk. This is the distance from a young star where temperatures drop low enough for carbon dioxide to condense into solid ice. In our solar system, that line sits farther from the Sun than the water ice line. Objects forming between these two boundaries would be carbon dioxide rich, but even then you'd expect water to be present as a significant component, not reduced to a mere 4%. Another possibility involves radiation processing. 3 Atlas spent billions of years in interstellar space bombarded by cosmic rays. This radiation can alter surface chemistry, breaking apart water ice molecules while leaving carbon dioxide relatively intact. Over enough time, you might create a surface layer enriched in carbon dioxide, but that would be a surface effect. Once the comet approaches the Sun and begins shedding material, you'd expect to dig through the processed layer and start seeing more typical compositions underneath. The spectroscopy shows no sign of this transition. The carbon monoxide ratio adds another puzzle. At 1.44 times the water abundance. It's elevated, but not as dramatically as the carbon dioxide. Carbon monoxide is even more volatile than carbon dioxide. It sublimates at lower temperatures. If the comet was simply warming up and releasing ices in order of volatility, carbon monoxide should appear first and in high abundance. Instead, it's carbon dioxide that dominates, with carbon monoxide as a secondary component and water trailing far behind. This chemistry suggests formation conditions unlike anything in our solar system. Either the comet comes from a protoplanetary disk with radically different composition than the one that formed our planets, or it underwent processes during its journey that transformed its makeup into something we've never encountered. And then there's the polarization. When light scatters off dust particles, it becomes polarized. The degree and direction of polarization depends on the size, shape, and composition of the particles, as well as the angle at which you're observing. Astronomers use polarization to infer properties of cometary dust that are difficult to measure directly. A team led by Zach Gray observed 3 Atlas through polarizing filters over several weeks. They measured polarization as a function of phase angle, the angle between the Sun, the comet, and Earth. The results were unlike any object in the solar system. 3 Atlas showed extreme negative polarization. At small phase angles, the polarized light was oriented perpendicular to what every other comet, asteroid, and dusty object displays. The magnitude of this negative polarization exceeded anything in the existing database. Negative polarization can occur when light scatters off particles with specific optical properties, but achieving the degree observed requires unusual combinations of size, composition, and structure. The dust grains would need to be larger than typical cometary dust, perhaps with complex internal structure or unusual refractive indices, or the scattering isn't happening in the way we typically model. If the dominant light source isn't scattered sunlight, but includes emission from the object itself, polarization signatures change. Fluorescence from gases can produce polarization patterns different from pure dust scattering. But again, that requires explaining what's emitting light and why. The polarization study, the inverted chemistry from Webb, the carbon chain depletion that somehow still allows a green glow. These observations combine to paint a picture of an object that violates expectations at every level. You can construct scenarios where each finding individually makes sense. A comet from a carbon dioxide-rich formation region, dust with unusual optical properties from extended radiation exposure, surface chemistry altered by billions of years in space. But explaining all of them simultaneously in a single object requires stacking unlikely conditions on top of each other. The comet would need to have formed in exactly the right location to be carbon dioxide dominated, then been ejected at exactly the right time to spend billions of years in interstellar space accumulating radiation damage, then happened to collect dust during that journey with optical properties unlike anything we typically see, then entered our solar system on a trajectory that brings it unusually close to multiple planets. The more specific the required conditions become, the less likely the scenario. And there's one more detail that deepens the mystery: the cyanogen detection. Cyanogen is a carbon-nitrogen compound. It's not uncommon in comets, but its presence is interesting because early observations detected it in 3 Atlas, while simultaneously showing a strong depletion of other carbon chain molecules like dicarbon and trirric carbon. Luis Salazar Manzano at the University of Michigan analyzed spectra from Kitt Peak Observatory. His team found evidence for cyanogen emission before the comet was close enough to the Sun to be strongly active. This suggests cyanogen was present in volatile form near the surface, easily released with minimal heating. But cyanogen production in comets typically correlates with the presence of complex organic molecules and carbon chains. Finding one without the others is unexpected, like discovering smoke without fire, unless the chemistry isn't following the pathways we assume. Unless the molecules weren't created through the standard processes of comet formation and evolution. Unless they were introduced through mechanisms we haven't considered. The chemical signature of 3E Atlas reads like a comet designed to confuse. Every measurement reveals properties that technically could be natural but collectively strain the boundaries of what natural processes produce. And while chemists debate isotope ratios and spectroscopists argue over emission line profiles, Aviba has been calculating something else entirely. Something that makes the chemistry question secondary to a more immediate concern about what this object might do next. Chapter 8, the Precursor Probe Theory. Lowe began with a simple geometric calculation. 3-2 Atlas passed within 29 million kilometers of Mars on October 3rd. But that's not the closest it gets to Mars' orbital path, the minimum orbit intersection distance, a measure of how close one object's trajectory comes to another's complete orbital path, sits at just 2.7 million kilometers. 2.7 million kilometers sounds vast. It's roughly 7 times the distance between Earth and the Moon, but in orbital mechanics terms, especially for an object travelling at 60 kilometers per s, is remarkably close. Close enough that a small adjustment in velocity could bring the comet into direct contact with Mars. Lowe calculated the numbers. A trajectory change of 10 to 15 kilometers per s applied during September would shrink that closest approach distance to 0. The comet would impact Mars or at minimum pass within the planet's atmosphere. Now, comets don't make trajectory changes that large. The outgassing thrust from a natural comet might produce velocity changes of a few hundred meters over months. Getting to 10 or 15 kilometers per s requires either a catastrophic fragmentation event or active propulsion. But here's what caught Lowe's attention. If 3 Atlas isn't a single object, if it's accompanied by smaller components, those components don't need to match the main object's velocity. A mothership releasing smaller probes can impart significant relative velocity. The probes separate following slightly different trajectories. While the main object passes Mars at 29 million kilometers, a probe with the right velocity vector could reach the planet. The Webb telescope measured the outflow velocity of gas, leaving 3 Atlas at 440 m/s. That's the speed of material naturally vaporizing from the surface. But if something were deliberately ejected, if a probe separated from the main body using mechanical force rather than thermal evaporation, it could achieve much higher speeds. A velocity of 10 km per s isn't unreasonable for a separation maneuver, is well within the capability of conventional rocket propulsion. Even a simple spring-loaded release mechanism could impart a few candy bears to a small object. So, Lowe asked, if 3I Atlas released precursor probes in September, could they reach Mars? The answer is yes, depending on timing and direction. A probe could arrive at Mars anywhere from a few days to a few weeks after separation. Now, we need to think about what that means practically. The Heresy camera on Mars Reconnaissance Orbiter was looking for 3 Atlas. It was calibrated to detect an object 5 to 10 kilometers across at 29 million kilometers distance. But Higher was designed to image Mars's surface. It can resolve features down to 30 centimeters. If a smaller object, say 100 mm across, passed closer to Mars within even a few hundred 000 km. HiRISE might detect it, except HiRISE was pointed at the expected position of the main comet. If a precursor probe came from a different angle, took a different path, it could approach Mars unobserved by the spacecraft specifically watching for 3I Atlas. The Perseverance rover's sky observations become more interesting in this context. Those images showing possible multiple objects, the ones Stephen Burns and others analysed, were taken during a window when both the main comet and any potential companions might be visible. If there were multiple fast-moving objects in those images, if that's not just processing artifacts or background noise, we might be seeing evidence of a dispersed system rather than a single compact nucleus. Lowe took the calculation further. He considered what happens after perihelion after the comet swings around the Sun and emerges on the other side. The object will be hidden from Earth-based observation from late October through most of November. It reaches perihelion on October 29th at a distance of 202 million kilometers from the Sun. During that closest approach, it'll be experiencing maximum solar heating, maximum radiation pressure, maximum stress on any structural components. If it's a natural comet, this is when we'd expect to see dramatic changes, increased activity, possible fragmentation. The nucleus could split, releasing fresh ice that dramatically brightens the coma. Outgassing rates could spike as subsurface volatiles reach critical temperatures. If it's something else, if it's capable of maneuvering, perihelion offers a strategic opportunity. The gravitational assist from passing close to the Sun could be used to alter trajectory. A small velocity change at perihelion translates to large position changes months later. This is how spacecraft use gravity assist to reach distant destinations efficiently. Lowe noted that with appropriate thrust at perihelion, 3I Atlas could adjust its path to intercept Earth. The object will be travelling retrograde opposite to the direction planets orbit. This geometry offers advantages for an intercept trajectory. You're not chasing a target. You're timing the collision between two objects moving toward each other. A velocity shift of 30 to 40 km per s during October could bring 3I Atlas or components of it to Earth between late December and early January. Is 30 to 40 km per s achievable for a natural comet? Absolutely not. For a spacecraft with propulsion, it depends on the mass and the engine. Chemical rockets would struggle with those numbers for something as massive as 3 Atlas. But we're talking about technology that potentially crossed interstellar space. Propulsion systems we can barely imagine. Lowe was careful in how he phrased this. He didn't claim 3 Atlas would maneuver toward Earth. He pointed out that the opportunity exists, that if the object has capability, this is when and how it would use it. And then he added something that got picked up by every news outlet covering the story. If 3 Atlas maneuvers toward Earth when it reappears from behind the Sun, financial markets may crash. Think about what that statement implies. Not just the immediate panic from news of an object heading toward our planet, but the deeper implications, confirmation that we're dealing with technology, that something artificial crossed interstellar space and is now approaching Earth, that we're not alone, and that whatever is out there knows we're here. Markets crash on uncertainty, on fundamental shifts in how we understand the world. The discovery of artificial interstellar technology would be the most profound uncertainty in human history, even if the object posed no direct threat. Even if its intentions were entirely benign. The knowledge that advanced civilizations exist and can reach our solar system would reshape every assumption underlying our economic, political, and social systems. Lowe's statement wasn't fear-mongering. It was recognition that the implications extend far beyond astronomy. This is why the Mars observations matter so much. This is why the silence from NASA and ASA feels significant, because right now 3 Atlas is approaching the point where if it's going to do something unexpected, this is the window, and we won't know what happened until it emerges from solar occultation weeks from now. potentially having changed course, potentially having released objects we can't track, potentially having demonstrated capabilities that force us to abandon the comfortable assumption that it's just an unusual comet. The Trojan horse. Lowe calls it an innocent-looking visitor that could carry devastating consequences hidden within its apparently natural exterior. Chapter 9. Behind the Sun, the danger window, Lowe crater scale. He calls it the Loeb scale, a ranking system from 0 to 10 that quantifies how likely an object is to be artificial rather than natural. 0 means definitively natural, a chunk of ice and rock following predictable physics with chemistry that matches known processes. 10 means definitively artificial, an object that displays unambiguous technological signatures that maneuvers in ways requiring propulsion that emits signals or exhibits structure impossible to explain through natural means. Most objects to 0 asteroids, comets, meteoroids, all the debris wandering through space scores 0 because nothing about them suggests technology. 1 Hyumua, the first interstellar visitor Loeb, ranks somewhere between 3 and 5 depending on which observations you emphasize. Its unusual shape, its non-gravitational acceleration without visible outgassing its tumbling motion. These features pushed it above 0 but not high enough to claim certainty. 3E Atlas Loeb currently ranks at 4. Not 0 because the anomalies are too numerous. The trajectory alignment with planets, the chemical inversions, the nickel without iron, the forward jet with no tail, the mass discrepancy. Each individually might be natural, but collectively they elevate the probability of something more. Not 10 because we lack definitive proof. No detected radio signals, no observed maneuvers, no photographs showing geometric structures. The object still behaves enough like a comet that natural explanations, however strained, remain possible. 4 sits in the uncertain middle, more likely than not to be natural, but with enough unusual features that the artificial hypothesis can't be dismissed. But that ranking could change dramatically based on what happens over the next few weeks. October 29th marks perihelion. The comet reaches its closest point to the Sun at roughly 1.4 astronomical units, just inside Mars' orbital distance. At that moment, from Earth's perspective, it will be directly behind the Sun. The Sun's angular diameter in our sky is about half a degree. 3 Atlas will pass within that glare zone. Ground-based telescopes can't observe it. Space-based observatories like Hubble and Webb need to avoid pointing too close to the Sun to protect their sensitive instruments. We go blind. The blackout extends from late October through most of November. The exact dates depend on viewing geometry and how bright the comet becomes, but conservatively, we lose direct observation for at least 3 weeks. 3 weeks where the object experiences peak solar heating, where any thermal stresses reach maximum, where if it's technological, it has privacy to do whatever it's designed to do. When it emerges, we'll be looking for changes. Brightness is the first indicator. If the comet fragments or undergoes a major outburst, it will brighten significantly. Solar system comets sometimes increase in brightness by several magnitudes during perihelion passage. If 3E Atlas does the same, it suggests natural processes are dominant. If it doesn't brighten, if it remains relatively stable or even dims, that's interesting. It might indicate a more durable structure, less vulnerable to thermal stress than typical comets. Trajectory is the second indicator. If the object emerges on a path consistent with gravitational predictions following the orbit calculated from Properian observations that supports the natural interpretation. If there's any deviation, any change in velocity or direction not explained by gravitational perturbations that moves it up the Loeb scale quickly, spectroscopy will reveal compositional changes. Did the surface chemistry shift? Are new materials exposed? Is the ratio of volatiles different from what we measured before, and structure? When 3E Atlas becomes visible again in early December, telescopes will immediately photograph it. Does it look the same? Is the forward jet still present? Is there evidence of fragmentation or splitting? Meanwhile, Low isn't just calculating possibilities, he's watching the sky. The Galileo project operates 3 observatories, one in Massachusetts, one in Pennsylvania, one in Nevada. They're equipped with wide-field cameras, infrared sensors, and automated detection algorithms designed to identify aerial phenomena that don't match conventional aircraft or natural objects. The project's primary focus is unidentified anomalous phenomena, UAP, what used to be called UFOs, but with 3 Islas approaching perihelion, ELO has added a specific monitoring protocol. If the object is a mothership, if it releases smaller probes toward Earth as it swings around the Sun, those probes would arrive weeks to months later. December through January becomes the window where unexplained aerial activity might spike. The Galileo project instruments will be running continuously, logging anything unusual, checking for patterns, looking for objects moving faster than satellites, displaying flight characteristics beyond current aerospace technology, appearing in numbers or with timing that correlates to 3I atlases, perihelion passage. It sounds like science fiction. It is science fiction in the sense that we're discussing scenarios pulled from speculative stories. But the difference is we're doing it with real data, real calculations, real objects that we can photograph and measure. If LOE is wrong, if 3E Atlas is simply an unusual comet and all the anomalies have boring explanations, the Galileo project will detect nothing unusual. The object will emerge from behind the Sun, slightly brighter, possibly fragmented, following its predicted path. The nickel emissions will be explained through some exotic chemistry. The trajectory alignment will be recognized as selection bias in which interstellar objects we notice life continues. If he's right, if even partially right, December becomes one of the most significant months in human history. Not because of invasion scenarios or hostile intent, Low is careful to avoid that framing. Even artificial objects can be benign scientific probes from civilizations with no interest in interference. But because confirmation changes everything, every assumption about our place in the universe gets rewritten. Every question about whether we're alone gets answered. Every decision about how we allocate resources, how we think about our future gets made in the context where we know that crossing interstellar space is possible, that other intelligences exist, that we are in the most profound sense not special. Yes, JUICE spacecraft currently on its way to Jupiter will observe 3E Atlas in late November. Between November 2nd and 25th, JUICE will point its instruments at the comet just after perihelion when it's emerging from the Sun's glare but still extremely active. JUICE carries cameras, spectrometers, and particle sensors. It's farther from the comet than Mars was, but it has the advantage of observing during peak activity when signatures are strongest. The data from JUICE won't arrive until February. The spacecraft is on the far side of the Sun from Earth, using its high-gain antenna as a heat shield, communicating through a slower backup system. So, we wait months for those observations to download and process. But they're coming, and they might show us what 3I Atlas was doing while hidden from Earth, what it looked like at its most active moment, whether anything changed that we need to understand. For now, though, we're in the dark, literally and figuratively. The object that's been puzzling astronomers for months is about to become invisible, hidden behind the overwhelming brightness of our star, doing whatever it does when nobody's watching. And when it comes back, if it comes back different, if it shows any sign of having done something intentional, Low's ranking moves from 4 to 5, maybe higher, and the questions we've been asking about whether it could be artificial shift to questions about what it wants and what we should do about it. Chapter 10. What we're not being told. There's a standard rhythm to how space agencies communicate discoveries, press releases get drafted, scientists give interviews, raw data populates public archives, social media accounts share highlights. The process is designed to be transparent, to build public interest, to justify the funding that makes these missions possible. When that rhythm breaks, when scheduled observations happen but results don't appear, when questions get deflected with vague statements about ongoing analysis, people notice. NASA's official page for 3 Atlas lists assets that observed or plan to observe the object: Hubble, Webb, TESS, Swift, Sphere-X, Perseverance, Mars Reconnaissance, Orbiter, Curiosity, Europa Clipper, Lucy, Psyche, Parker Solar Probe, Punch, SOHO, and ESA's JUICE. It's an impressive array. Practically every functional space telescope and planetary mission got pointed at this object at some point, but the data releases don't match the observation schedule. Webb spectroscopy from August appeared quickly, published as a preprint within weeks. Hubble's July image became public. Ferrex's results on carbon dioxide emissions were shared. Then October hit and the flow stopped. The Mars observations from October 1st through 7th should have been the easiest to release. Mars orbiters routinely make their images public within days. The High-C website typically updates with new Mars surface photos every few days, sometimes daily during active observation campaigns. Yet nothing from the 3 Atlas flyby has appeared. The SA operates under different administrative structures than NASA. Different funding sources, different oversight, different public communication requirements. When both agencies go silent simultaneously on the same target, it suggests coordination. Coordination can mean collaboration. Scientists from both agencies working together agreeing to wait until all data is analysed before making statements. This is reasonable for complex observations where preliminary results might be misinterpreted. Or coordination can mean consultation, discovering something unexpected that requires discussion about how to present it. What context to provide, what additional verification to complete before going public. The silence from Simeon Schmaus, the astrophotographer who claimed to see early glimpses in October 1st images, adds another layer. Amateur observers typically share their findings eagerly. The community thrives on rapid discussion, on crowdsourced verification, on collaborative analysis. When someone goes quiet after making an intriguing claim, it usually means one of two things. Either they found an error and are embarrassed, or they found something significant and are preparing a more detailed presentation. Schmaus hasn't retracted his observations. He hasn't posted corrections. He simply stopped commenting. Meanwhile, amateur astronomers continue working with whatever data is available. The publicly posted Perseverance images from those October nights remain accessible. Anyone with image processing software can download them, stack them, look for moving objects. Multiple independent analysts have now reproduced Stephen Burns's finding of at least one fast-moving object consistent with 3 eyelays. The debate focuses on whether additional objects are present. Some see them clearly. Others attribute the apparent additional lights to artifacts from stacking algorithms to cosmic ray hits that coincidentally appear near the comet's path to background asteroids. Without the high-resolution data from his and the ESA orbiters, without official confirmation or denial, the question hangs unresolved. What we're seeing is a pattern, official channels constrained by review processes and institutional caution. Amateur observers filling the gap with varying degrees of rigor and reliability, and an object that continues generating more questions than answers. Consider what we still don't know despite months of observation. The exact size of the nucleus. Estimates range from less than 1 kilometre to over 10 kilometres, depending on assumptions about aldo, and whether we're seeing primarily the nucleus or an extended dust coma. The rotation rate. Some observations suggest rapid rotation. Others show no clear periodicity. Understanding how fast it spins tells us about structural integrity, about whether it's a single solid body or a loose aggregate. The source regions of outgassing is material venting from discrete jets or from broad areas of the surface. Discrete jets suggest localized volatile deposits or structural features. Broad emission suggests more uniform surface composition. The degree of fragmentation, if any. Has the nucleus split into multiple pieces? Are there companion fragments travelling alongside the main body, or is it structurally intact? These are fundamental questions that the Mars observations were supposed to answer. HiRISE at 30 km resolution should easily distinguish between a single compact object and a fragmented or multi-component system. The spectroscopy from Mars Express and ExoMars should reveal regional composition variations if they exist. The instruments functioned. The observations were executed. The data exists somewhere in agency archives. We're just not seeing it. There is innocent explanations. Data pipelines genuinely backed up by technical issues. Scientists conducting thorough analysis before making statements. Bureaucratic delays unrelated to the content of the observations. There are less innocent explanations. Uncertainty about how to characterize unexpected findings. Consultation about whether preliminary observations warrant broader discussion before formal publication. Institutional hesitancy to make claims that might later require embarrassing retractions. And there are concerning explanations. Discovery of features that challenge comfortable assumptions. Evidence of structures or behaviors that don't fit natural categories. Observations that, if released without context, would generate exactly the kind of speculation and panic that agencies work hard to avoid. We don't know which category applies. That's the problem. The absence of information creates a vacuum that speculation fills. What we can say with certainty is that the next few weeks matter enormously. 3E Atlas will emerge from behind the Sun in late November or early December. Ground-based telescopes will immediately photograph it. Amateur astronomers will be watching. Professional observatories will allocate time. If it looks the same, if its trajectory matches predictions, if its brightness and spectral signature remain consistent with what we measured before, the natural comet explanation strengthens considerably. If anything has changed, if there's evidence of maneuvering or structural modification or unexpected brightening or new compositional signatures, the artificial hypothesis gains support. JUICE will observe it in late November during peak post-Perrine activity. Europa Clipper, currently en route to Jupiter, might also get observations depending on geometry and mission priorities. These spacecraft see the comet from angles and distances unavailable to Earth-based instruments. Their data will eventually arrive, eventually be processed, eventually inform our understanding. But eventually isn't now. Right now, we're in a gap between what's been observed and what's been shared, a gap between amateur discoveries and official confirmation. A gap between the questions we're asking and the answers that exist somewhere in data files we can't access. And while we wait in that gap, 3I Atlas continues its journey, approaching the Sun, heating up, becoming more active, potentially doing things we won't know about until weeks from now when it reappears and we see what changed. So, here we are waiting, watching an empty sky where something extraordinary is hidden behind our Sun. 3 Atlas is out there right now, closer to our star than it's been in billions of years, absorbing gigawatts of solar energy, potentially fragmenting, potentially maneuvering, potentially doing nothing more dramatic than what comets have done since the solar system formed. We've traced its path from the outer reaches of space, calculated where it was when the WOW signal reached Earth, measured the impossible ratios in its chemistry, documented the metals that shouldn't be there, mapped the tail that points the wrong way. We've counted the statistical improbabilities, stacked the anomalies, and arrived at a place where certainty feels impossibly distant. Maybe it's just a comet. Unusual one, granted, but ultimately a natural object following natural laws. The anomalies will resolve. The missing data will appear and clarify. December will come and the object will look exactly as expected. Slightly brighter, following its predicted path, confirming that the universe still makes sense. Or maybe we're watching something that will rewrite every assumption we have about our place in the cosmos. Either way, the next few weeks will tell us, and we'll be here when they do. Thank you for staying with this story, for following these questions into uncertainty, for being willing to sit with mystery instead of demanding easy answers. If you found this valuable, consider liking and subscribing so you're here when the object emerges and we finally learn what we've been looking at. As always, this content is for educational and entertainment purposes. The science is real, the observations are documented, but the interpretations remain speculative. We're exploring possibilities, not making definitive claims. Do your own research, question everything, including what you've heard here. For now, 3 Atlas moves in silence behind the sun. December approaches. The amateur telescopes are ready. The professional observatories have time allocated. The Galileo Project instruments are recording. And somewhere out there in the darkness, an object from another star carries on its journey, indifferent to our questions, our theories, our hopes, and fears about what it might represent. Sleep well, dream of distant stars, and remember that the universe has always been stranger than we imagined. Good night. Picture this right now, at this very moment, 620 light-years away, a planet the size of Jupiter is eating. Not slowly, not carefully, but violently. 6 billion tons of gas and dust every single second, flowing into something that should not exist, something that blurs the line between what we call a planet and what we call a star. Meanwhile, closer to home, on a world we have studied for decades, a robot the size of a car has found something in a rock that might be the fingerprint of alien life. And in laboratories across Earth, scientists have just shattered a barrier that has stood for the entire history of quantum computing, building a machine that can run forever, theoretically speaking, opening doors we thought were decades away. But here is what makes this week truly strange. While we're making these cosmic discoveries, we're also discovering that our own bodies harbour secrets we never suspected. Fat tissue, the kind we carry every day, has been caught red-handed, sending chemical messengers directly into our brains, messengers that may be building the very plaques that steal our memories. And if we go back far enough in time, before any of this mattered, before humans, before dinosaurs, before the first tree ever grew, there was a kingdom that ruled this planet for nearly 1 billion years. Not animals, not plants, fungi, the hidden architects that built the world we inherited. This is not science fiction. This is this week. If you find yourself pulled into these mysteries, hit that like button and subscribe. Then tell me in the comments where you are listening from, what time it is there, and which of these discoveries shakes your understanding of reality the most. And if you want to help our community grow, share this on X, Facebook, Reddit, or your messenger. Thank you for always having our back. Chapter 1, The Leopard-Spotted Rock. On the 23rd of July 2024, a machine named Perseverance pressed a drill bit into a rock on Mars. The rock had a name, Chava Falls, chosen by the team back on Earth who'd been watching this particular stone for months. They had reasons. The rock sat at the edge of what used to be a river valley, a channel that once carried water rushing into a crater that held a lake more than 3.5 billion years ago. But it was not the location alone that made them stop. It was the pattern on the surface. Spots. Dark circles with pale rings scattered across the reddish stone like the markings on a leopard's fur. No one had seen anything quite like it before. The drill collected a core sample, a cylinder of rock about as thick as a pencil, and sealed it inside a tube for potential return to Earth. Then the real work began. The rover carried instruments that could peer into the chemistry of the rock without opening the tube. What they found sent ripples through this scientific community that is still spreading today. The spots contained iron and phosphate. Between the pale bands of calcium sulfate, there appeared to be traces of hematite, the mineral that gives Mars its red colour. But here in this rock, something had turned the red to white. That kind of chemical reaction releases iron and phosphate. And those reactions can provide energy, the kind of energy that microbes use. On September 10th, 2025, a paper appeared in the journal Nature. The authors had spent a year examining the data, running tests, checking and rechecking their findings. They described the presence of two specific minerals, vivianite and grage, iron phosphate and iron sulfide, on Earth. These minerals form in oxygen-poor environments where microbes are consuming organic matter, where life is using chemistry to survive. The patterns matched, the chemistry matched. Everything about this rock suggested a process that on our planet would be unmistakably biological. The acting administrator of NASA held a press conference. After a year of review, he said they could not find another explanation. This very well could be. He told the world, the clearest sign of life we have ever found on Mars. Not proof, not yet, but the closest thing to it we have ever held in our robotic hands. The media exploded. Headlines screamed about alien microbes and ancient Martian life. But the scientists were more careful. They used a term that sounds awkward but carries enormous weight. Potential biosignature. A thing that might have been made by life but requires more study before anyone can say for certain. Here is where the story takes a frustrating turn. The sample sits inside Perseverance's belly, sealed in its tube, along with 24 other samples collected from different locations across Jezera crater. To know for sure what made those leopard spots, scientists need to bring that rock home. They need to examine it with instruments far more sensitive than anything we can send to Mars. They need mass spectrometers and electron microscopes and tools that fill entire laboratories. There is a program designed to do exactly this. It is called Mars Sample Return. But the program is in trouble. The projected cost ballooned to somewhere between 8 and 11 billion. The timeline stretched to 2040 or beyond. Then came changes in political administration, shifts in priorities, budget constraints. As of today, Mars Sample Return exists in a kind of limbo, neither dead nor fully alive. So, we have a rock on Mars that might contain evidence of ancient life, and we have no clear path to bring it home. Chapter 2. The planet that eats like a star 620 light-year from Earth in the constellation Chameleon. There is an object that should not behave the way it does. It has a designation rather than a name. Chia 1107 7626. Music, a string of numbers and letters that astronomers use to catalogue things they find in the cosmos. This object has mass somewhere between 5 and 10 times the mass of Jupiter. Our solar system's giant. That mass puts it firmly in the category we call planets. But it does not orbit a star. It drifts alone through space. One of what we believe are trillions of rogue planets wandering the galaxy untethered, floating in the darkness between stars. For years, scientists thought these rogues were cold, quiet, dormant objects that formed around a star and were kicked out, or perhaps collapsed from clouds of gas too small to ignite fusion, forever dim and unremarkable. Char 7 proved them wrong. In the spring of 2025, astronomers pointed the European Southern Observatory's Very Large Telescope toward this object. They saw something calm, a young world still surrounded by a disk of gas and dust, the leftover material from its formation. The disk was feeding the planet slowly through a process called accretion, material falling onto the surface, adding to its mass bit by bit. This is normal. This is how planets grow. Then by August, everything changed. The planet began to devour its disk, not gradually, violently. The accretion rate spiked 8 times faster than it had been just months before. 6 billion tons of material every single second, pouring into this lone world, floating in the void. To put that in perspective, imagine the entire mass of Mount Everest disappearing into this planet every few seconds. For at least 2 months, this feeding frenzy continued, and when the paper was published on October 2nd, 2025, it was still going. The lead researcher, a scientist named Victor Al-Mendros Abad, said something that captures the strangers perfectly. People may think of planets as quiet and stable worlds, he explained. But with this discovery, we see that planetary mass objects freely floating in space can be exciting places. Exciting is perhaps an understatement. What CHAR 11107 is doing has only been observed before in young stars and brown dwarfs. Objects massive enough to have complex magnetic activity. This is the strongest accretion episode ever recorded for a planetary mass object ever in the entire history of astronomy. Here is where it gets stranger. The team detected signs of magnetic fields driving this infall of material. Strong magnetic fields funneling gas and dust toward the planet's surface like invisible highways in space. This is a process we associate with stars, not planets. Stars have the mass and internal dynamics to generate powerful magnetic fields. Planets, especially rogue planets drifting alone, should not. Yet, here it is happening, observable, undeniable. The discovery also revealed water vapor in the planet's atmosphere during the burst and hydrocarbon molecules that shifted in shape as the feeding intensified. Signatures of heat and turbulence reorganizing the chemistry of the disk. Scientists are now asking a question they thought they had answered. Where do rogue planets come from? The 2 main theories have been ejection, where a planet forms around a star and gets kicked out by gravitational interactions or direct collapse, where a cloud of gas in space collapses under its own gravity, but never gets massive enough to become a star. If ejection is the answer, these planets should be cold, dead, their formation disks long gone, but CHAR 107 still has its disk. It is still growing, is behaving like something that formed in place. Condensing from a cloud just like a star would, only stopping short of the mass needed for fusion. This blurs a line we thought was clear. What is the difference between the smallest stars and the largest planets? We defined it by fusion, by whether an object can sustain hydrogen burning in its core. But if objects in the planetary mass range can form like stars, grow like stars, and use magnetic fields like stars, then maybe the line is not as sharp as we believed. Maybe there is a spectrum, a gradient between planet and star, and rogue worlds like CHAR 107 live somewhere in the middle, defying our categories. The researchers believe we are watching planet formation happen in real time, seeing a world build itself in the darkness between stars, and the process is far more dynamic, far more violent than anyone predicted. Chapter 3, The Machine That Never Stops. Inside a laboratory at Harvard University, there is a machine that has been running for over 2 hours. This might not sound remarkable until you understand what the machine is. It is a quantum computer. And for the entire history of quantum computing, these devices have had a fatal flaw. They stop not because someone turns them off, but because the quantum bits, the qubits that make them work, simply vanish. They decohere, as physicists say, meaning they lose their quantum properties and become useless. Early quantum computers could run for milliseconds. The most advanced machines stretched that to around 13 seconds. Then they had to restart, reset, begin again. The Harvard team, led by a professor named Mael Lucan, built something different. In September of 2025, they published their findings in the journal Nature. Their quantum computer has 3000 qubits, and it can run continuously without stopping, without restarting, for as long as they choose to keep it powered. Theoretically, it could run forever. This is not an incremental improvement. This is a fundamental breakthrough that changes what quantum computers can do. Here's the problem they solved. Quantum computers work by manipulating atoms or subatomic particles, holding them in delicate quantum states where they can represent multiple values at once. This is what gives quantum computers their power, their ability to solve certain problems exponentially faster than classical computers. But these quantum states are fragile. They require extreme cold, often near absolute zero. They require isolation from vibrations, from stray electromagnetic fields, from anything that might disturb them. And even with all that protection, the qubits eventually fail. They leak information, they collapse. The quantum state dissolves and the computation ends. The Harvard team spent 5 years working on this problem. They developed a method using what they call an optical lattice conveyor belt and optical tweezers. These are tools made of focused laser light that can grab individual atoms and move them around with extraordinary precision. The breakthrough was figuring out how to replenish the qubits while the machine is running. As qubits leave the system, new atoms are injected to replace them. The machine can add 300,000 atoms per second, far exceeding the rate at which qubits are lost. There is now fundamentally nothing limiting how long these quantum computers can run. One of the researchers, a man named Tout Wang, said something striking in an interview. "There is still a way to go and scale from where we are now," he explained. "But the roadmap is now clear based on the breakthrough experiments we've done here at Harvard. Clear roadmap. Those words matter in a field where progress has been uncertain and timelines have repeatedly slipped." Another collaborator, a physicist from MIT named Vladnik, was even more specific. Before this, he said it was believed that continuously running quantum computers were at least 5 years away. Now it seems much closer. More on the horizon of 2 to 3 years. Think about what that means. Within 2 to 3 years, we might have quantum computers that operate like the classical computers we use every day. Not machines that run for seconds and restart, but machines that stay on, that accumulate results, that can tackle problems requiring long-sustained computation. The implications ripple across dozens of fields. Drug discovery, where quantum computers could simulate molecular interactions that are impossible to calculate classically. Cryptography, where they could break encryption schemes that protect global communications. Artificial intelligence, where they could optimize neural networks in ways we cannot currently achieve. Material science, financial modeling, climate prediction, any domain where complexity exceeds the reach of traditional computing. But there is another layer to this story. Google also made news in the quantum world recently using a 58-qubit quantum computer to create and observe something called a flow topically ordered state. A phase of matter that was theorized but never seen. It exists only when a quantum system is driven rhythmically, periodically, creating a non-equilibrium state that cannot be captured by traditional physics. They watched exotic particles transform in real time, confirming theories about how matter behaves when pushed far from equilibrium. These are the kinds of experiments that quantum computers enable. Not just fast calculations, but entirely new ways of exploring physics itself. Chapter 4. The fat that speaks to your brain. There is something happening inside your body right now that scientists have only just discovered. Your fat tissue, the adipose that cushions your organs and stores energy, is not sitting quietly. It is talking, not in words, obviously, but in chemical messages. Tiny packages wrapped in membranes that travel through your bloodstream. These packages are called extracellular vesicles, and they carry cargo. Lipids, proteins, genetic instructions. They slip through the walls of blood vessels, They cross barriers that most molecules cannot penetrate, and some of them, researchers have now proven, make it all the way into your brain. A team at Houston Methodist, led by a scientist named Stephen Wong, published their findings on October 3rd, 2025. They collected fat tissue samples from people who were lean and people who were obese, isolated the vesicles these tissues released and examined what was inside. The lipid cargo was different. Specific fat molecules were more abundant in vesicles from obese individuals. Molecules with names like lisophosphatidylcholine and sphingerin. Then they did something clever. They exposed these vesicles to amyloid betapeptides, the proteins that form the sticky plaques found in the brains of Alzheimer's patients. The vesicles from obese tissue made the proteins clump together faster, significantly faster. The lipids they carried accelerated the aggregation process, the very process that is believed to drive neurodegeneration. This is not correlation, this is mechanism. The researchers showed that fat tissue can send signals directly into the brain, and those signals can alter how quickly the hallmark pathology of Alzheimer's forms. Obesity has been known as a risk factor for Alzheimer's for years, but the link was always murky, indirect, mediated through things like inflammation or insulin resistance. This study draws a direct line. Fat tissue releases vesicles. The vesicles cross the blood-brain barrier. The vesicles carry lipids that promote plaque formation. It is a pathway, a biological circuit connecting the body's energy storage to the brain's most devastating disease. At almost the same time, another team at Purdue University published related findings. They were looking inside the brain itself at cells called microglia, the immune cells that are supposed to protect neurons. In healthy brains, microglia patrol constantly, clearing debris, fighting infections, maintaining balance. But in Alzheimer's brains, the microglia closest to amyloid plaques were different. They were swollen, filled with lipid droplets, fat accumulating inside the cells themselves. The researchers, led by a professor named Gareth Chopra, found that these fat-filled microglia could not do their jobs. They could not clear plaques. They could not protect neurons. They were essentially paralyzed by their own lipid burden. The team traced the biochemical pathway. When microglia encounter plaques and inflammation, they start producing free fatty acids. Normally they would use these as fuel, but in the disease state, something goes wrong. An enzyme called DGAT2 converts the free fatty acids into tresylglycerol, a stored form of fat, and it does this in such large quantities that the microglia become overloaded. The lipid droplets pile up. The cells cannot move. They cannot function. Chopra described these accumulations as lipid plaques, a term that echoes the amyloid plaques everyone focuses on, but represents a different problem. A parallel pathology that has been overlooked for over 100 years. Here is the twist. The researchers tested two molecules, one that blocks DGAT2 and one that promotes its degradation. The degradation approach worked. It reduced the fat buildup. It restored the microglia's ability to eat amyloid plaques. It improved markers of neuronal health in animal models of Alzheimer's. This suggests a new kind of treatment, not targeting the amyloid itself, but targeting the fat metabolism that cripples the brain's defenses. It opens a door that pharmaceutical companies have not been walking through, a door that connects Alzheimer's research to lipid biology, to metabolic disease, to the 40% of the US population living with obesity. Think about the implications. Alzheimer's has been studied for decades as a problem of protein misfolding of amyloid and tau tangles of plaques and neuroinflammation. Hundreds of drugs have been designed to remove plaques or prevent their formation. Most have failed. What if the reason they failed is that they were addressing the symptom, not the cause? What if the real driver is hiding in plain sight in the fat that fills our cells and sends messages we never knew were being sent? Chapter 5. The kingdom that prepared the world. Before there were forests, before there was grass, before the first moss clung to a wet rock near the ocean's edge. Something else was already here, not waiting, working, breaking down stone, cycling nutrients, building the chemical foundation that would make everything else possible. We think of life on land as beginning with plants, green pioneers colonizing a barren surface. But the surface was not barren when plants arrived. It had been prepared for hundreds of millions of years by a kingdom we barely notice. Fungi. On October 1st, 2025 researchers from the Okinawa Institute of Science and Technology published a paper in Nature, Ecology and Evolution that rewrites the timeline of terrestrial life using a combination of fossil evidence and a novel technique involving horizontal gene transfers. Genes that jump sideways between species rather than passing from parent to child. They trace the origins of fungi back much further than anyone expected. The common ancestor of all living fungi existed somewhere between 1.4 billion and 900 million years ago. To put that in perspective, land plants appeared around 470 million years ago. Fungi were diversifying for possibly a billion years before the first plant ever set root. This is not a small revision. This changes the entire story. Complex multicellular life. Organisms made of many cells with specialized jobs, evolved independently exactly 5 times on Earth. Animals, land plants, fungi, red algae, and brown algae. Each group developed its own mechanisms for cells to stick together, communicate and organize into tissues. For most of these groups, fossils provide clear timestamps. Animals show up around 600 million years ago in formations like the Adidian with their distinctive impressions. Red algae appear possibly as early as 1.6 billion years ago in ancient seaweed like fossils from India. But fungi leave almost no fossils. Their bodies are soft, thread-like, quick to decay. Dating their evolution has been a puzzle with missing pieces. The research team, led by a scientist named Gergely Solacey, used horizontal gene transfers as temporal clues. When a gene from one fungal lineage jumps into another, it establishes a rule. The ancestor of the donor lineage must be older than the descendant of the recipient lineage. By identifying 17 such transfers and combining them with the sparse fossil record, the team constrained the fungal timeline with unprecedented precision. What emerged was a picture of a kingdom that dominated Earth's continents for an almost incomprehensible span of time. Imagine what that means. For hundreds of millions of years, possibly approaching a billion, fungi were the most complex life on land. They were not alone. Algae existed in the oceans and likely in shallow coastal environments. Bacteria formed microbial mats, but fungi were different. They were doing chemistry that nothing else could do. They secrete enzymes that break down rock, liberating phosphorus and other nutrients locked in minerals. They form networks, malleable threads that connect distant patches of soil, shuttling resources across landscapes. They partner with other organisms, exchanging nutrients for sugars, creating symbioses that benefit both sides. The researchers found evidence that some early fungi had enzymes capable of breaking down pectin, a component of plant cell walls, as far back as 1.2 billion to 800 million years ago. This suggests they were interacting with algae, perhaps helping them survive in the harsh transition zone between water and land. By the time plants finally evolved and began moving on to continents, they did not find a blank slate. They found a world conditioned by fungal activity, a world with primitive soils with nutrient cycles already established with chemical pathways already flowing. This flips the pioneer narrative. Plants did not conquer land alone. They inherited a world fungi had been engineering for eons. And when plants did arrive, they formed partnerships with fungi almost immediately. We call these partnerships mycorrhizae. and they're everywhere. 90% of land plants today have fungal partners living in or around their roots, trading sugars for minerals. It is possible, even likely, that plants could not have colonized land without these partnerships. And those partnerships may have roots, both literal and evolutionary, stretching back to when fungi first began interacting with algae in the primordial shallows. Chapter 6. The Vinegar That Fooled the World. In March of 2024, a small clinical trial was published in a journal called BMJ Nutrition, Prevention and Health. The study came from Lebanon, conducted by researchers at Holy Spirit University of Catholic. It involved 120 young people, average age 17, all of them overweight or obese. The participants were divided into 4 groups. 3 groups drank apple cider vinegar each morning in doses of 5, 10 or 15 milliliters, mixed with water and taken before food. The 4th group received a placebo, fake vinegar that looked and tasted similar but lacked the active ingredient etic acid. The trial lasted 12 weeks. The results, according to the published paper, were remarkable. The vinegar drinkers lost weight, not a little, 6 to 8 kilograms on average. With those taking the highest dose seeing the largest drops, their body mass index fell, their waist and hip measurement shrank, their blood glucose, triglycerides, and cholesterol all improved. The paper suggested that apple cider vinegar slowed gastric emptying, promoting feelings of fullness and reducing appetite. It presented charts and statistical analyses showing clear, significant differences between the vinegar groups and the placebo group. The journal published the study with a press release. Media outlets around the world picked it up. Headlines proclaimed a simple, cheap solution to obesity. Apple cider vinegar, a common pantry item, suddenly positioned as a weight loss miracle. The study went viral. Articles multiplied. Social media influencers began promoting daily vinegar shots. The apple cider vinegar market, already valued at over $1 billion, saw renewed interest. People cited the study in forums, in blog posts, in conversations with friends. It had the weight of peer-reviewed science behind it, published in a journal affiliated with the BMJ Group, a respected name in medical publishing. But some researchers were skeptical from the start. A man named James Heathers, a research integrity consultant, began examining the paper shortly after it appeared. What he found troubled him. The age and body mass index distributions across the 4 groups were nearly identical. Statistically, this is unlikely. When you randomly assign people to groups, you expect some variation. But the groups in this study looked too similar, as if they had been perfectly balanced rather than randomly distributed. Heathers published an analysis in May of 2024 outlining what he called implausible patterns in the data. He pointed out that if the results were true, apple cider vinegar would be 50% more effective than drugs like Ozempic, medications that cost thousands of dollars and require prescriptions. A tablespoon of vinegar achieving better results than cutting-edge pharmaceutical interventions strained credibility. Other researchers raised concerns through letters to the journal. The study had not been registered in advance, a requirement under BMJ Group editorial policy designed to prevent selective reporting of results. The statistical methods were unclear. Attempts to replicate the analyses from the published data failed. The BMJ Group's content integrity team launched an investigation. They referred the paper to independent statisticians, asking them to evaluate its reliability and attempt to reproduce the findings. The statisticians could not. They identified multiple analytical errors. They found irregularities in the dataset that suggested the underlying data needed independent scrutiny. The raw numbers did not add up. On September 23, 2025, 18 months after the original publication, the journal retracted the paper. The retraction notice was blunt. The results were unreliable. Multiple errors had been identified. The data could not be verified. The authors in their response said the errors were honest mistakes and agreed with the decision to retract. But the damage was done. For a year and a half, the study had been cited as evidence. It appeared in systematic reviews, meta-analyses that pull results from multiple studies to draw broader conclusions. One such review published shortly before the retraction relied in part on the invalid data to suggest that apple cider vinegar might help with weight management. That review is now compromised, built on a foundation that includes fabricated or deeply flawed results. An editor at BMJ Group, a woman named Helen MacDonald, made a public statement. Tempting though it is to alert readers to an ostensibly simple and apparently helpful weight loss aid, she said, "At present the results of the study are unreliable, and journalists and others should no longer reference or use the results of this study in any future reporting." But how many articles remain online uncorrected, still citing the retracted research? How many people changed their behaviour based on information that turned out to be false? Chapter 7. The Moon's Divided Heart. Our moon has two faces and they are not the same. Anyone with a telescope can see this. The near side, the face that always points toward Earth, is covered with dark patches called Maria, ancient lava plains that filled impact basins billions of years ago. The far side, hidden from our view until spacecraft circle behind it, looks completely different. Fewer Maria, more craters, a landscape that appears older, less processed by volcanic activity. For decades, this asymmetry has puzzled planetary scientists. Why would one hemisphere of the moon be so different from the other? They are part of the same body, formed from the same material, shaped by the same cosmic history. Or so we thought. On October 3rd, 2025 researchers published an analysis of lunar samples collected from the far side by China's Chang'e 6 mission. These are the first samples ever returned from that hemisphere, and they tell a story that contradicts what we believed about the moon's interior. The rocks are rich in minerals that form from magma, molten rock that cooled and crystallized. But the chemistry is off. The samples contain fewer heat-producing elements, fewer radioactive isotopes of potassium, thorium, and uranium than rocks from the near side. This is significant because those elements are what keep a planetary interior hot. They decay over billions of years, releasing energy that can drive volcanic activity that can melt rock and send it flowing to the surface. The researchers concluded that the far side formed from cooler magma, not just slightly cooler, substantially cooler. This suggests that the moon's interior is not uniform. It is not a simple layered sphere with a crust, mantle, and core arranged symmetrically. There is a symmetry built into its deep structure. The difference in composition and temperature between the near side and far side that dates back to the moon's formation. The leading theory for how the moon formed involves a giant impact. Early in Earth's history, roughly 4.5 billion years ago, a Mars-sized object collided with our planet. The impact was so violent, it vaporized rock, creating a disk of debris in orbit around Earth. That debris coalesced, pulled together by gravity, forming the moon. But the process was not smooth or uniform. The moon was likely molten at first, a sphere of magma cooling slowly over millions of years. As it cooled, denser minerals sank, lighter minerals floated, creating layers. The new findings suggest this process happened differently on the two hemispheres. Perhaps the near side facing Earth received more heat from tidal forces from the gravitational pull of our much larger planet flexing and warming the interior. Perhaps the distribution of radioactive elements was uneven from the start, concentrated more heavily on one side. Whatever the cause, the result is a moon with a divided heart. This matters for more than just lunar geology. It tells us something about how rocky bodies form and evolve. We tend to assume symmetry to model planets and moons as spheres with uniform layers. But if the moon, which is relatively small and simple compared to a planet, can have such profound internal asymmetry. What does that mean for other worlds? Mars has hemispheres that look wildly different. The northern lowlands smooth and flat, the southern highlands ancient and cratered. Could Mars also have an asymmetric interior with different thermal histories on each side? What about exoplanets? The thousands of worlds we've discovered orbiting other stars, we cannot see their interiors, but if asymmetry is common, our models might be fundamentally wrong. The samples also revealed something else. They confirmed the volcanic activity on the far side ended earlier than on the near side. With fewer heat-producing elements, the far side could not sustain volcanism as long. It went quiet while the near side was still erupting, still filling basins with lava. This creates a kind of geological record, a timeline written in rock, showing how the Moon's heat budget declined over billions of years. By studying these samples, researchers can constrain models of planetary cooling or how long it takes for a world to freeze internally to become geologically dead. Chapter 8. The ice that hides an ocean. Saturn has dozens of moons, but one of them keeps drawing scientists back, keeps generating headlines, keeps suggesting that we might not be alone, even in our own solar system, Enceladus. A small world only about 500 kilometers across, wrapped in ice so bright it reflects nearly all the sunlight that touches it from a distance. It looks pristine, frozen, dead. But in 2005, the Cassini spacecraft flew close enough to see what was really happening. Enceladus is not dead. It is erupting from cracks near its south pole. Enormous plumes of water vapor and ice particles shoot into space, geysers that rise hundreds of kilometers above the surface. These are not occasional events. They're continuous, constant, fed by something beneath the ice, an ocean, a global ocean of liquid water tens of kiln deep, sitting beneath a shell of ice perhaps 20 to 30 kilometers thick. The ocean is kept liquid by tidal heating, the same kind of gravitational flexing that keeps Jupiter's moon Io volcanically active. Saturn's gravity squeezes and stretches Enceladus as it orbits, generating friction in the moon's interior, producing heat, melting ice that should, by all rights, be frozen solid. Cassini flew through the plumes. It tasted them, analysed their chemistry with onboard instruments. The findings were extraordinary. Water, obviously, but also salts. Evidence of rock-water interactions happening on the ocean floor. Silica particles, tiny grains of silicon dioxide that form when hot water interacts with rock at temperatures above 90 degrees. And organic molecules, simple ones at first, methane, carbon dioxide, compounds containing carbon but not necessarily indicating life. Then in later flybys, more complex molecules, propane, ethane, acetylene, and now, according to fresh analysis of Cassini data published on October 2nd, 2025, even more complex organics locked inside the ice grains. The researchers reanalyzed data that Cassini collected years ago, applying new techniques and models to extract information that was not visible in the initial studies. What they found were organic compounds with multiple carbon atoms, molecules that on Earth are associated with biological processes, though they can also form through non-biological chemistry. The presence of these compounds does not prove life, but it strengthens the case that the conditions inside Enceladus's ocean could support life. Liquid water, energy from tidal heating, organic molecules, rocky surfaces where chemistry can happen. These are the ingredients we look for when we search for habitable environments. Here's what makes Enceladus so tantalizing. The ocean is not isolated. It is connected directly to space through those plumes. Anything dissolved in the ocean water, any molecules, any cells, if they exist, can be carried up through the cracks and ejected into space. This means we do not need to land on Enceladus, drill through kilometres of ice, and lower instruments into a dark ocean. We just need to fly through the plumes and collect samples. In principle, we could detect life without ever touching the surface. NASA and other space agencies have been discussing missions to do exactly this. Spacecraft designed to orbit Saturn, make repeated passes through the plumes, and analyze the material with instruments far more sensitive than what Cassini carried. But there's a frustration here. Similar to the Mars sample return problem, these missions are proposed, studied, designed, and then delayed. Budget constraints, competing priorities, technical challenges, political shifts. The earliest any dedicated Enceladus mission might launch is the mid to late 2030s. That is a decade or more away. Meanwhile, the evidence accumulates. Every new analysis of Cassini data reveals more complexity, more hints that Enceladus is not just habitable, but might actually be inhabited. We have a world with an ocean, with energy, with organic chemistry spewing its secrets directly into space for us to sample. And we are waiting. Saturn has other moons with subsurface oceans. Titan, the giant with its thick atmosphere and methane lakes, almost certainly has a water ocean deep beneath its icy shell. Jupiter's moon Europa has an ocean that might contain twice as much water as all of Earth's oceans combined. Ganymede and Callisto likely have oceans as well. Our solar system, it turns out, is not dry. It is wet, filled with hidden seas locked beneath ice, oceans that have been there for billions of years, stable, shielded from radiation, possibly teeming with life we have not yet imagined. Chapter 9. The Hunter Before Blood. When you think of a leech, you probably picture something unpleasant. A dark slug-like creature attaching to skin, feeding on blood, leaving a wound that bleeds longer than it should because of anticoagulants in the leech's saliva. Leeches are parasites, organisms that survive by taking from others. They are soft-bodied, difficult to love, and generally absent from the fossil record because soft tissue rarely preserves. But on October 2nd, 2025, researchers announced the discovery of a leech fossil that changes everything we thought we knew about these creatures. It is 430 million years old, pushing the origin of leeches back 200 million years earlier than any previous evidence. The fossil comes from a formation that preserves exceptional detail, capturing not just the outline of the animal, but the structure of its body segments, the shape of its head, even hints of its internal anatomy. What shocks paleontologists is not just the age. It is what the fossil reveals about what leeches were before they became parasites. This ancient leech was not a blood feeder. It was a hunter, an active predator with jaws and a body built for movement in open water. It lived in the ocean, not in freshwater ponds or terrestrial environments where modern leeches are found. It was in every sense a different kind of animal from the leeches we know today. Modern leeches belong to a group called Hyodudinera. Within the larger film Annalita, the segmented worms, they're closely related to earthworms and marine bristleworms, all sharing a body plan built from repeating segments. But leeches lost the bristles, lost the rigid gait that other annelids use for traction. Instead, they evolved suckers, one at each end of the body and a muscular, flexible form that allows them to inch along surfaces or swim with undulating waves. Most importantly, many leeches evolved specialized mouthparts for piercing skin and feeding on blood, a lifestyle that requires biochemical adaptations, enzymes to prevent clotting, and aesthetics to avoid detection, all packed into saliva that turns a simple bite into a sophisticated parasitic strategy. But 430 million years ago, none of that had happened yet. The fossil leech had a different body, longer, more streamlined, built for speed rather than attachment. Its jaws were sharp but not adapted for piercing skin. They were for grabbing, for holding on to prey, for tearing apart small invertebrates in the water column. This was a carnivore. an ocean predator that swam actively and hunted other animals. The researchers who studied the fossil, publishing their findings in a peer-reviewed journal, described it as a window into a lost world, a time when leeches were not the parasites we despise, but were legitimate hunters in marine ecosystems. This discovery forces a rethinking of leech evolution, the parasitic lifestyle. The blood-feeding behaviour came later. It was not the ancestral condition. Somewhere in the intervening millions of years, some lineage of hunting leeches shifted strategies. Perhaps they started scavenging on dead animals, feeding on wounds. Perhaps they transitioned to feeding on live animals opportunistically, taking small amounts of blood when the chance arose. Over time, those opportunistic feeders became specialists, refining their mouth parts, their saliva, their behaviour until they became the obligate parasites we see today. But the fossil shows that leeches began as something else entirely, and it raises a question. Are there still hunting leeches out there? Undiscovered lineages that never made the transition to parasitism? The ocean is vast and poorly explored. We have better maps of the surface of Mars than of the deep-sea floor. New species are discovered constantly. Strange worms and bizarre invertebrates that do not fit existing categories. It is entirely possible that somewhere in the deep ocean, in a trench or canyon we have never visited, there are leeches that still hunt, that still live the way their ancestors did 430 million years ago. The fossil is a reminder that evolution is not a straight line, not a march toward complexity or improvement. It is a branching tree with lineages diverging, experimenting, some succeeding, and some going extinct, each adapting to the environment and opportunities available. Chapter 10. How words rewrite reality. There is a kind of manipulation so subtle, so insidious that the victim does not realize it is happening until their grip on reality is already loosened. It has a name: gaslighting. The term comes from a 1938 play, later a film in which a husband systematically manipulates his wife into questioning her own perceptions, her own memory, her own sanity. He dims the gaslights in their home and then insists they have not changed. He hides objects and claims she misplaced them. He contradicts her recollections until she no longer trusts herself. The play was fiction, but the phenomenon it depicted is devastatingly real. On October 2nd, 2025 researchers at McGill University and the University of Toronto published findings that reframe gaslighting not as simple deception, but as a learning process rooted in how our brains handle conflicting information. The study, published in a peer-reviewed neuroscience journal, describes gaslighting as a form of associative learning gone wrong, where repeated exposure to false information from a trusted source can override direct sensory experience. Your brain, they explain, is constantly trying to build a model of the world. A mental representation that predicts what will happen next. This model is updated based on two streams of information: what you perceive directly through your senses and what you learn from others, especially people you trust. Under normal circumstances, these two streams complement each other. You see a red apple. Someone tells you it is a red apple. The information matches and your model is reinforced. But gaslighting creates a conflict. You see a red apple. Someone you trust tells you it is green. Now your brain has a problem. It must decide which source of information to weight more heavily. If the person contradicting you is someone you depend on, someone who's been reliable in the past, someone with social or emotional power over you, your brain may choose to trust them over your own eyes, not consciously, not as a deliberate decision, but as an automatic adjustment in the learning algorithm your brain uses to navigate the world. The researchers used brain imaging and behavioral experiments to study this process. They showed participants a series of images and then had confederates, people working with the experimenters, provide false information about what the images contained. The confederates were presented as experts, as people with special knowledge. creating a context where their statements carried authority. Over repeated trials, the participants began to doubt their own perceptions. When asked to recall what they had seen, they increasingly reported the false information provided by the Confederates, rather than what they had actually observed. The brain scan showed activity in regions associated with conflict resolution and memory reconsolidation, areas that activate when the brain is rewriting stored information to incorporate new data. This is not stupidity. This is not weakness. This is the brain doing what it evolved to do, which is to learn from others. Humans are social animals. We survive by sharing information, by trusting the knowledge of our community. If everyone in your group tells you that a certain plant is poisonous, you do not need to eat it yourself to find out. You trust them, and that trust keeps you alive. But this same mechanism, this social learning system, can be weaponized. If someone with power over you consistently contradicts your experience, your brain may begin to prioritize their version of events over your own memory. You start to doubt yourself. You question your perception